Welcome to The Explainer. Today, we're diving into a challenge that could literally rewrite the rules of digital security. We're talking about the race to make blockchains safe from quantum computers. And no, this isn't science fiction anymore. It's a very real storm brewing on the horizon, with billions of dollars, and the very idea of digital trust hanging in the balance.
Okay, so here's our game plan. First, we'll look at how blockchains like Bitcoin create trust in the first place. Then we'll get into the quantum threat that could, shatter that trust. After that, we're going to explore the two main rescue missions, one that reinforces our current systems and another that builds something totally new. And finally, we'll tackle the real-world headache of making this huge switch and the heated debate over how much time we actually have.
All right, first things first. How is a system like Bitcoin supposed to be a digital fortress? What's the secret sauce that makes it so tough to crack with today's best computers?
It all boils down to this thing called public key cryptography. Think of it like this. You have two keys. One is your private key, that's your secret. You use it to sign off on transactions, proving you're you. The other is your public key, which you can share with anyone. It acts like a lock that only your private key can open. It's a super clever system for proving who's who online.
But that's not all. The next layer of security is how these transactions are all linked up. They get bundled into blocks, and each new block gets stamped with a unique digital fingerprint, a hash, of the one that came before it. This creates this unbreakable, interlocking chain. To go back and change just one tiny detail, a hacker would have to redo the work for that block and every single block after it. It's designed to be just computationally brutal.
So this fortress, it seems pretty much unbreakable. But here's the catch. It's only unbreakable for the kinds of computers we have now. There's a totally new kind of machine coming, and it plays by a whole different set of rules.
And that leads us to the billion-dollar question, right? What happens when a computer comes along that's so powerful it can shatter the very math that our entire digital world is built on? What if those unbreakable digital locks could suddenly be picked?
This slide really pinpoints the two big attacks. First, you've got Shor's algorithm. You can think of this as the ultimate skeleton key. It's a quantum recipe that can take a public key and figure out the secret private key from it. Game over for your wallet. Then there's Grover's algorithm. This one attacks the chain itself, making it way faster to find the right hash to forge a block. It could let an attacker literally rewrite history. The stakes here are just staggering. We're talking about roughly 4 million Bitcoin. That's more than a quarter of all the Bitcoin out there, sitting in wallets that are basically sitting ducks. Their public keys are exposed, making them vulnerable. And yep, that includes the famous million coin stash believed to belong to Bitcoin's creator, Satoshi Nakamoto.
And here's the really chilling part. This isn't just some problem for the future. There's the strategy called harvest now, decrypt later. It means bad actors can be recording encrypted data right now, hoarding it, stockpiling it, with the plan to crack it all open the second they get their hands on a powerful enough quantum machine. In a way, the attack has already begun.
So how do we defend the fortress? Well, the first path to safety is maybe not what you'd expect. It doesn't actually require us to build quantum computers. Instead, it's all about reinforcing our existing systems with new kinds of math that are built to be quantum-proof from the get-go.
Welcome to the world of post-quantum cryptography, or PQC. Researchers have been developing a bunch of these new families of algorithms. They all run on the computers we have today, but they're based on math problems that are believed to be super hard for both our computers and future quantum ones. And after a big, years-long competition, the US government standards body, NIST, has started picking winners, with lattice-based crypto emerging as a major frontrunner.
So what is this lattice-based cryptography? Well, it's essentially a totally new kind of mathematical lock. Instead of relying on factoring big numbers, its security comes from the insane difficulty of finding the shortest possible path between points in a super complex, multi-dimensional grid. It's a problem that, as far as we know, is a nightmare to solve, even for a quantum computer.
Okay, so that's path one. Path two is, well, it's a lot more radical. It's more futuristic. This one is all about just abandoning the old fortress and building a brand new, almost magical one from the ground up, using the weird and wonderful rules of quantum mechanics itself.
This approach leans right into quantum mechanics.
It starts with qubits. Now, a normal computer bit is a 0 or a 1. A qubit can be a 0, a 1, or both at the same time. It's called superposition. It also uses entanglement, what Einstein famously called spooky action at a distance, where two particles are linked and whatever you do to one instantly affects the other, no matter how far apart they are.
Now, even on this path, there are kind of two flavors. The one that's closer to reality is a hybrid system. You might use a normal, classical blockchain, but use a quantum trick like quantum key distribution to send keys around securely. The much more ambitious idea is a fully quantum blockchain, where the data, the links, the whole shebang is made of entangled quantum states. Right now, that's still deep in sci-fi territory.
So we have two potential solutions, right? We can upgrade the math we have, or we can build brand new quantum systems. But, and this is a big but, here comes the twist. Choosing the solution is actually the easy part. The real challenge is putting it into practice.
Yeah, the real-world problem, the one that keeps cybersecurity experts up at night, isn't just about picking the winner in the PQC race. It's about building systems with something they call crypto agility. All it means is that our entire digital infrastructure, from banks to blockchains, has to be flexible enough that you can unplug the old crypto and plug in the new stuff without the whole system crashing down.
And getting that kind of agility is a huge job. Organizations have to start by just figuring out what cryptography they're even using. Then they have to automate how they manage all their keys, because doing it by hand is way too slow and risky. They need to build their system so the crypto part is like a Lego block you can swap out. And they've got to get in the habit of rotating their keys all the time. It is a massive undertaking.
So that brings us to today. This is not some far-off academic discussion. The race to get ready for this quantum future is happening right now. It's happening in corporations, in university labs, in open source projects. And believe me, it is a messy, passionate, and incredibly high-stakes race.
And this timeline shows you exactly why everyone's feeling the pressure. I mean, the basic science is old, but the pace of actual progress is just accelerating like crazy. You have these huge milestones, Shor's algorithm in the 90s, Google's quantum supremacy claim, NIST announcing the new standards. They're all happening closer and closer together. The curve is getting steep.
This has sparked a really fierce debate online and in the industry. On one side, you've got people arguing that the threat is right around the corner. They point to public roadmaps from companies like IBM that say they're aiming for cryptographically relevant machines by the early 2030s. And they highlight projects like quantum-resistant ledger, QRL, which was built to be quantum safe from day one, basically saying, what are you all waiting for?
But then, on the other side of that argument, you have plenty of smart people who think a quantum computer that's actually stable enough and powerful enough to be a real threat is still decades away. They argue that we have plenty of time to develop and roll out the fixes before there's a real crisis. So in the end, the question really isn't if this huge transition is going to happen. It's how and when. The technology that can break our world is on a clear path of development. The solutions to protect us are taking shape. But the real test, the great unknown, is whether our vast, complex, interconnected digital world can actually make the switch before it's too late. The race is on.